So myself Geetha, working as assistant professor in Department of EEE in Satyabama Institute of Science and Technology, Team to P University. I would like to give a lecture on op-amp applications. Like you might be familiar with operational amplifier. So I would like to tell you what is an amplifier first. Amplifier is nothing but if suppose you give an input, you will be liking to have if 10 volt input you give, and you will be liking to have 20 volt output. So if you want to have a DC amplification, you can go with an operational amplifier. Now today I would like to give you a few applications based on this amplification factor. Now we have a component or device called operational amplifier, which is going to be designed with a smaller IC with 8 pins. These 8 pins are going to be differentiated, I mean classified into like offset null, ground, plus VCC, minus VCC, and input 2 terminals for input and 1 for your output terminal. So now the first slide tells you what is the description we are going to see about your series. Now I will give you an intro of an operational amplifier, then we will go on with few applications like inverting amplifier, non-inverting amplifier, summing amplifier, voltage follower, and a differential amplifier, where there are 2 input terminals you have, as I have told you in the operational amplifier. These 2 input terminals are being denoted with minus and plus, and you have one output terminal, and this output terminal will give you the amplified input factor. So this operational amplifier symbol, which is shown in your slide, will help you to know the symbol like minus and plus. Tells you minus represents your inverting terminal and plus represents your non-inverting terminal, and V out, which is represented at the end of your symbol, tells you that this is the point where you get the output. And parallelly you could see the pin diagram of it, which represents inverting input, non-inverting input, and the output, and 2 pins for your IC. Now as I have told you, this IC contains 8 pins, but most probably we will be using only the 5 pins, which is most preferable ones, that is 2 for input, 1 for output, and 2 for power supply. Now going on for the next applications like inverting amplifier. If you could see, you can see the op amp which is being provided with V in, input voltage is provided at the negative terminal, and you have a feedback resistance of RF, and you have an internal input resistance of RL. Now what happens is that I have represented V2 and V1 into the negative and the positive terminal, and this V2 represents the node voltage which connects your feedback resistance and your input resistance RN. This V2 tells you that it is a virtual node voltage. Why do I call this as a virtual node voltage is that you could see that parallelly a positive terminal which is being grounded with a 0 voltage. This 0 voltage will be available at the node called X in the slide, and over there this is being given as a virtual earth summing point that will take a voltage of 0 volt where you have it in your positive terminal. Now we will go on for the analysis of this circuit. Now this analysis you could see, since I have not provided any input to the positive terminal, you can see that only one input V in is moving throughout your operation, and this V in moving via Rn and RF, and you reach your output. Now the current through this particular series element, you can just try to see like V in, the difference between your voltages V in minus your V out divided by Rin plus Rf, which is the additive part of your resistance. Since your node voltage V2 is 0, because of this I could say that I is equal to V in minus V naught divided by Rn plus Rf, provided if you could go with a nodal voltage at node 2, you can say just to see that V in minus V2 divided by R1 will be equal to V2 minus V out divided by RF. Now if you just try to equate it, you will be reaching your V out to be equal to minus RF by R1 into V in. This minus RF by R in says that this is your gain of your operational amplifier which we are designing it now. Now if you just see V out is equal to minus of RF by R in into V in. Now this, suppose you just give a value of RF to be 1 kilo ohms or 1 ohms or R in to be 1 ohms, you can see that V out will be equal to minus of V in. Now what it says that whatever the input you provided at the negative terminal, your output of your operational amplifier will be of a negative value. Positive input you provide, you get a negative value in the inverting amplifier circuit. So I have provided an example for you to understand, for the understanding purpose. You can just see over here, I have substituted Rin to be 10 kilo ohms and RF to be 100 kilo ohms. You might wonder, like, you have Rin as 10K and RF as 100K. If you want an unity gain, you have to go with RF equals to Rin. So here I am not going on with a gain. You can just see Rin as 10 and RF as 100K. Now what is the formula for your gain? It is equal to minus RF by Rn. Substitute your values of Rf and Rn, you will be getting it as minus 10, and this 10 is nothing but your gain of your amplifier circuit, and you have a rise or the drop with respect to decibels you speak, it is 20 log to the base 10 of your gain value. Now this is about a few small example for the clarification of the inverting amplifier. Now what do I try in the next state is that you have two input terminals, one is negative and positive. Now I have tried to give an input to the negative terminal and tried to find what is going to be the gain of it, and now let me go on for giving the input to the positive terminal. If suppose you just look into the circuit, there is a small change in your circuit, like the positive terminal which you have grounded in the previous case, it is being given with an input voltage of V in. Now where you have given your V in the previous circuit, you can see that it is being grounded into it. Now after grounding it, go for the analysis. If you go for the analysis, you can see a potential divider circuit into the circuit when you go for grounding your negative, grounding your negative terminal. So next analysis speaks like, if it is going to be a potential divider circuit, you go on for finding the voltage at 1. So what it says is, potential divider says that the total voltage at the output into the same arm resistance divided by the summation of the two resistances which you have. So now V1 is found to be R2 by R1, R2 plus RF into V out. Now you can see a summing point where you have given as V1. Now since we have spoken in the earlier case, like this is going to be acting as an virtual node, you can see the parallel voltage is being given as an V in. Now if you just give V in as the voltage, then the node which is being called as a virtual node will also be called as a virtual node. Now the voltage which your node has got, the same voltage will be available at that particular node also. So that particular node voltage, I represent it as V in. Now rearranging your equation, substituting V1 to be equal to V in, you can see your equation as we all are familiar with the gain formula, right? It is V out divided by V in. Substituting your cancellation parts and looking into the output or gain of your non-inverting amplifier, you can see that R2 plus RF divided by R2. What it says is that when you go for an input of 1 volt, you go on for getting an output of 2 volt. Now this is one kind of amplification you can see in the non-inverting amplifier. Like if you want to go with a gain greater than 1, you have to go on with only non-inverting amplifier. And you can also see what is the inference we have provided from the inverting amplifier and the non-inverting amplifier is that whatever the input you give it in the inverting amplifier, it is giving an output of 180 degree out of phase shift. Now you can see the non-inverting amplifier, if you give an input of V in, you get the same output. So what it means that you don't have any phase shift in the output provided you have an amplification in the output. So the gain differs for the inverting amplifier and the non-inverting amplifier. So your gain of the inverting amplifier doesn't go beyond 1 and the gain of the non-inverting amplifier will go beyond 1. So this is about the inverting and non-inverting terminal. Now I have given an input to the negative terminal and I have given to the positive terminal, which acts as the two input terminals of my op amp. Now what do I have to do is that next case I go on for giving an input, more than one input to the same terminal. When I go on for giving a more than one input to the same terminal, what happens? How does my op amp reacts to it? No other changes we are going to do it. The virtual node is going to be called as a virtual node as it is. provided you are providing more than one input to the negative terminal. Now you could see there in the summing amplifier, you can see that you have a voltage of V1, V2 and V3 with an internal resistance of Rn, Rn and Rn. I have an equal resistance value. It takes 3 different currents, I1, I2 and I3, and you have a same feedback resistance Rf which takes a current of If. Now you can see the same virtual node, since my positive terminal is grounded, this virtual node will carry a voltage of 0 volt, and also you can also have an inference from the previous inverting amplifier. So looking into it, the negative terminal, whenever you give any input, it will give an gain of minus Rf by R1. So now you have 3 different resistances over here. If you go on with analysis, now this V out divided by V in will give you Rf by Rn. Same way, V out divided by V2 will give you same Rf by Rn. Since all the resistances values which you have provided is the same, you can have the gain also the same for it, but you can see that the input voltages which you have applied is going to be different. Now going on with the analysis, as I have told you, your feedback current If is equal to the summation of the currents I1, I2 and I3, because you have connected all the resistances in parallel. So now if you have to go on with I1 and I2 and I3, you have to go on for finding, you should know what is the voltage applied to that particular resistance. Now you can just see that V1 is the voltage applied to the first resistance Rn, and V2 is the voltage applied to the second resistance, and V3 is the voltage applied to the third resistance. Provided you can also have a different resistances value as you wish. Now you can just see that I1 is nothing but V1 by Rn, I2 is nothing but V2 by Rn, I3 is nothing but V3 by Rn. Substituting all into the equation, you can see that If is equal to minus of additive part of the all values which you have noted down. Now your V out will be equal to what? So since we have already notated that your V out will be equal to the non-inverting gain into the inputs which you have provided. So now what is your gain of your non-inverting, inverting amplifier? It is minus Rf by Rn. Now minus Rf by Rn into the input you give, what happens is that input voltage, what you have found it as the input voltage, it is nothing but additive part of the voltages which you have given, V1 plus V2 plus V3. Now you can just see V out is represented as minus of your feedback resistance Rf by Rn into V in, V1 plus Rf by Rn into V2, and it goes on. Now if suppose you want to change the value of Rn, you want to change it into an average amplifier, you want to make your summing amplifier into an average amplifier, what you can provide is that you can go on for substituting your Rf to be equal to 1 by 3 times of Rn, or you can also substitute Rn to be equal to 3 times of Rf. Then your summing amplifier can be called as an average amplifier. Now this is how we have bulked your number of inputs to the same positive terminal or to the negative terminal. Now I have given an input to the negative terminal and I have got a gain of minus Rf by Rn into my input voltages. Now you can try for giving the inputs to the positive terminal, whereas your gain will be forwarded to 1 plus Rf by Rn. That is the only change you can infer from your negative and positive terminal in case of your summing amplifier. If suppose you provide your inputs to the negative terminal, your amplifier will be called as an inverting summing amplifier. You provide your number of inputs to the non-inverting terminal, you call it as a non-inverting summing amplifier. Now what do I go for try in the next state is that, so you have an example for summing amplifier. I have given 2 inputs V1 and V2 with 2 millivolts and 5 millivolts, and you have got 1 kilo ohms and 2 kilo ohms with the 2 different resistances value I have provided as I have told you here, and Rf is equal to 10 kilo ohms I have provided. Now I am aware that A1 is the gain of the amplifier, my input voltage V1 is active and V2 is inactive. Now what is the voltage of my V1? It is 2 millivolt. Now 2 millivolt along the path of 1 kilo ohms towards your output will give me a gain of minus 10. Now you can go with the next input, it is 5 millivolt towards your 2 kilo ohms. Along your 10 kilo ohms feedback, you will be getting an output of minus 5 as the gain. Now what happens is that V out will be equal to additive part of your input 1 and the input 2. Now you will be getting it as minus 10 plus minus 5. So now you can see that the total gain of the summing amplifier as minus 45 millivolt. Now you can just see, this is a small example which I have provided you with different values. If you go on with providing a same value, you can have the gain to be simple additive part. Now that is why we call this as a summing amplifier. Next, what do I go for try is that I don't give any input, let me go for a negative feedback just without a resistance value. I just go for only feedback and give my input. Most probably this acts as a buffer. Wherever I just need an isolation part, I go with this voltage follower circuit, where whatever the input I give, the same output I will be getting it, right? Either it is positive or the negative inputs. I give a positive input, I get a positive output. I give a negative input, I get a negative output. This is called as an voltage follower. Follower in the sense, whatever you give, the thing will be at the output terminal. Now this is going to be called as an voltage follower. Now what do I do is that I have separately provided inputs to the positive terminal, I have separately provided inputs to the negative terminal, and I have also grouped my inputs and have provided to the negative terminal, and you can also do it for the positive terminal. Now let me go for giving inputs to both the terminals at a time. When I just go for giving inputs to both the terminals at a time, so what happens, it is no more called as an inverting amplifier or a non-inverting amplifier. So I give both inputs, one to the negative terminal and one to the positive terminal. What might be your output? Output will be what? It is going to be your difference between your voltages V1 and V2. Now you can see the circuit which you have with you now. You have V1 as the input 1 given to the negative terminal and V2 as the input 2 which is provided to the positive terminal, and you have the same feedback resistance here represented as R3. Now you can just go on for the analysis of this differential amplifier. Here you have a node called VA and VB. Now here we are also having a virtual node which is VA and VB. Now if you go on with the analysis, you may be more clear in the analysis. Now if you just say, I have to go on for finding I1 separately. I1 is the current entering your node A. So what will be I1? I1 is nothing but V1 minus VA divided by V1. This is mere nodal analysis which we go on for. This nodal analysis will help you to go on for the analysis now. So now go for the finding of IF. IF will be equal to VA minus V0 divided by R3. Now go for the nodal analysis at the other node called B. You go with, it is V2 minus VB or VB minus V2. It is depending on the direction of the current which you have it into your circuit. Now you can just see your I1 is given as V1 minus VA divided by R1, and I2 is provided as V2 minus VB divided by R2, and IF is nothing but your difference in the output voltage to your node voltage divided by R3. Now you can just see your summing point, that is your VA and VB is your nodal points which you have with you there. When you go on for writing the equation at node B, when you go on for writing equation at node B, it represents a potential divider circuit. When you go for a potential divider circuit, you can easily make your expression as the resistance, the same resistance R4 which is connected to your node B divided by summation of the resistances, that is your R2 and R4 into the total voltage V2. Now VB is given as V2 into R4 divided by R2 plus R4. Now what will be VA? VA is nothing but your virtual node. Whatever the node B has got, the same voltage your node A is going to have. Now VA is equal to VB. Now whatever the node voltage you have found it for VB, you can substitute it for VA also. Now what is this V2 now? So when you go on for the differential amplifier, we need to analyze that or assume that there are two voltages. When you go for analysis alone, you should understand that one will be active and one will be inactive. Depending on that particular concept, we go on for the analysis considering or assuming that V2 is equal to 0 when we go for finding your V out with respect to V1. So V out will be minus of V1 into R3 by R1. This is for the case like V1 is active and V2 is inactive. Now next case we will go on with V1 is inactive and V2 is active. When V2 is active, what will be your output? It is nothing but V2 into your potential divider resistances value. Now you have two outputs, one with active, as superposition theorem says. Either your voltage, one is active and one is inactive, you go for, and the additive part will give you the total voltage. This is the concept behind your superposition theorem. Now your output voltage will be the additive part of your V out at your when your second pin is active and V out when your third pin is active. Now you go on for the additive part, you can see that V out of B minus V out of A. Now substituting all the values, we could reach that the total output voltage is equal to R3 by R1 into the difference between the applied voltages V2 minus V1. Now I would like to come to a conclusion now, like we have seen an applications of inverting amplifier, non-inverting amplifier, summing amplifier and voltage follower followed by a differential amplifier. Now this is all mere applications of telling you like whatever inputs you give without any operations, how do you get a different output in your op-amp. There are few other applications where you can have your output after making any mathematical operations like differentiation, integration, and you can also generate an waveform also along with without any inputs. You can also provide your outputs using your op-amp. In the forthcoming series, I would like to give you few other applications like a triangular wave generator using an operational amplifier, or a square wave generator using an operational amplifier. You can also generate a pulse which can be used for giving it as an firing pulse for your power electronic circuits. Now this op-amp plays a major role in providing you either a pulse or a differentiated value or a change in your waveform. So you want a square pulse to be changed to a spike, or you want a square pulse to be changed into a triangular wave, you can go with the operational amplifier applications. Now thank you everyone for watching this. If you have any doubts, feel free to ask. Thank you.